Alright guys, we have a warm-up here for 2.4. So again, take a moment, work through this warm-up first, and then check your answers when you're done. So I'm going to go ahead and give you a moment to pause the video. Okay, so the warm-up here, number one, we have the intersection. Again, what we're doing, we're going to write a conditional statement from each of the following. So we need to write a statement out from this. And when they say conditional, that means if then. So we have to have if. So I'll go ahead and put that down here. We have to have the if, and then we're going to have the then. So if whatever, your hypothesis, then your conclusion. So we have the intersection of two lines is a point. So if two lines intersect, then they intersect at a point. Now when I'm writing this, just understand there are different ways you can actually set this up. So if you didn't write it this way, that's fine. There are many different ways to do it, but you need to have if and then it needs to say the same thing that this is trying to say. Alright, number two, an odd number is one more than a multiple of 2. So again, an odd number is one more than a multiple of 2. So if a number is one more than a multiple of 2, then it is odd. Again, there are different ways to write it, but it should say something like that. I'll give you a basic idea of how you should be saying it. Alright, the next one I'm going to put up top here. This one says write the converse of the conditional. So again, the converse, what we're looking at is you have this hypothesis. There we go. The hypothesis here, Pedro lives in Chicago. And we have the conclusion, he lives in Illinois. Okay, so what the conditional means we're going to flip that around. So again, we have if P then Q. Again, they want the converse. And the converse is if Q, then P. So if I go ahead and write that up, I'm going to have if, and I'm going to take the conclusion, which is he lives in Illinois, and I'm going to say, or Illinois, it's not Illinois, if Pedro lives in Illinois, then I can take now the hypothesis and make it the conclusion. Then he lives in Chicago. Okay, so in this case you'll see that I took the hypothesis and conclusion and I flipped them around. Now they're saying find its truth value. So if Pedro lives in Illinois, then they're saying that here at the converse he has to live in Chicago. And this one you would say false. Again, if you don't know why, you would say something like he could live in another city in Illinois. Although I've been to Illinois before and there's a lot of farmland, so he could live on a farm maybe, I don't know. If you're not in Chicago, there's a lot of farmland in Illinois, just so you know. Okay, so there's your warm-up. So we'll kind of go at this point, kind of take this and understand these concepts. Obviously, these are all from Chapter 2, and we're going to go into the lesson now for 2.4. All right, so the lesson goal for today is to be able to write and analyze a biconditional statement. So obviously, you're going to need to know what a biconditional statement is. So that's going to be one of the things that you need to make sure you take away from this lesson. Okay. So the biconditional statement is a statement, I'm going to kind of reading right from here. So a biconditional statement is a statement that can be written in the form P if and only if Q. This means if P then Q and if Q then P. Now the key on this when we're doing both of these is when you have this statement and this statement, to have a biconditional, we have to state that both must be true. If they're not both true, you can't write the biconditional. Okay, so they say you combine a conditional statement and its converse, you create a biconditional. Well, it's only if you combine a true conditional statement and its true converse. There we go. Okay, so that's the key on this. As you look at everything that we're going to be going over here, the key is that these conditional statements have to be true, or else you cannot form the biconditional. So that's a biconditional, and that's what we're going to be going over today. All right, so this is the way you will write it. And I like to use symbolic notation because it's so much easier when you're talking about a concept to just use the symbols instead of writing out the long sentences. So this is your biconditional statement. That means if P, then Q, and if Q, then P. That's telling you both of these are true. The conditional and the converse are both going to be true. So if you have this written out, you can have it written out as P if and only if Q. So the things that I would want you to take from this means P if and only if. That looks like it's the same word, so let me fix that. Okay, P if and only if Q. Or you could say it like this. I'll say and or. You can go P, and then when you have these two F's, that means if and only if. It's a shorter way of saying that as well. So there's lots of different ways you can do biconditionals, and there's so many ways. It's such a common type of phrase. But again, if and only if means it's a biconditional. So again, as you're writing your notes here, let's get this all organized. Understand what a biconditional is, okay, and how it's formed. Again, biconditional is formed if you have if P then Q, and if Q then P are both true. Then you can write it in this form: P if and only if. That's what the arrow means. Q. And again, make sure you understand what the double arrow means and how you say it. Okay, so that's going to be what we're going to be going over today. Obviously, we need to find truth values of statements, conditional statements, and their converses to see if they can be a biconditional or not. All right, so here it says write the conditional statement and converse within the biconditional. So what we have here is we're starting with a biconditional. And again, the reason why we know it's a biconditional is if and only if. So we need to then be able to take this and rewrite it as a conditional and its converse. So first off, let's talk about what is P and what is Q. So here we go. These are your two parts. Actually, let me change the second one. I like to color code when I get an opportunity. So we're going to color code. So the first part to this sentence, this Cho is a member. This is going to be your P. You can also call it, obviously, your hypothesis. The second part we'll call Q, which is your conclusion. And we're going to use that to write our conditional, if P, then Q. So and again, if you're doing a conditional statement, it is always if then. So if Cho is a member, then he has paid the $5 dues. Okay, and that's your conditional statement. From there, you can also write the converse. If Q, then P. So if, and now we're going to flip it around, but let's use proper English as we do it. Instead of starting the sentence off with a pronoun, we need to say who the pronoun refers to, which is Cho. So if Cho, instead of he, has paid the dues, and again, they're the $5 dues, then he is a member. Now the only other thing to really add to this is truth values, because again, remember, if you actually have a biconditional, both these statements need to be true. And as you can see, this would be true. If he's a member, he must have paid the dues. And you can say the same thing here. If he has paid the dues, then that means he's a member. Both of these are true statements. And that's why we can say this biconditional statement: Cho is a member if and only if he has paid the dues. That's the only way he's going to be a member. And that's kind of what that if and only if is trying to tell you. All right, next example says for each conditional, we're going to write the converse in a biconditional statement. Now remember what I've been saying before. If you can write, the only way you can write a biconditional statement is if the conditional and its converse is true. So that's why we're always combining them both. So in this case, we have 5x minus 8 equals 37. That's our hypothesis. Our conclusion is x equals 9. So what we're going to do is we're going to flip those two around to write its converse. I'm going to flip the hypothesis and the conclusion. So this is the converse of the statement. I have if x equals 9, then 5x minus 8 equals 37. So again, you want to look at the truth value here. If 5x minus 8 equals 37, then does x equal 9? Yes, it does. So the converse, again, if x equals 9, then that means that you can say that 5x minus 8 does equal 37. These are both true. So we got our truth value for both of those. Now I can write the converse. So now I can say, here's how you write your converse. You're going to be P if and only if Q. So you start by writing the hypothesis. You don't need an if and a then here. It's P if and only if Q. So you have 5x minus 8 equals 37 if, and here's the shorthand that you can do on this. I'm going to allow this. Do IFF. That means if and only if x equals 9. And again, as a reminder, that means if and only if. Alright, so there's example A. This next statement, same difference. Just, we got a sentence this time. I can't write that at all. Man, that was terrible. Don't worry, I'll fix it though. Okay, so I'm going to highlight here. I'm highlighting my hypothesis to get started. And then my conclusion, I'm going to highlight as well. And again, I'm doing that just so you can keep track. Make sure you are able to recognize when we're dealing with an hypothesis and when we're dealing with a conclusion. Because in order to flip them around, write converses, inverses, contrapositive, things like that, we need to be able to recognize the different parts. So that's kind of where we're at this point. I have a hypothesis and conclusion. I'm going to flip them around to write the converse statement. In order to write a biconditional, I have to have the converse as well and make sure they're both true. So here we go. If. Now, I'm going to take my conclusion and make it now my hypothesis. My conclusion right now is they are congruent. What is they? Well, they is the two angles. We need to use proper English. So if two angles are congruent, then they have the same measure. So in this case, we have a statement, a conditional statement, and we have a converse of that conditional statement. And again, this is true. Two angles are the same, have the same measure, they're congruent. And if two angles are congruent, they have the same measure. These are both true. So therefore, I can write my biconditional. And again, here's how we write it. P if and only if Q. So I'm going to go two angles are congruent if and only if, again I'm using this shorthand notation, if and only if they have, oops, and I flipped it around. I'll fix it though, so follow me here. Right, oop, didn't mean to do that. Okay, so again we're going to do our P if and only if Q. If you notice what I did here, I wrote two angles are congruent, and that's my conclusion, I need to do it this way. Two angles have the same measure if and only if they are congruent. And that'll fix that. There we go. That's better. There's your biconditional. In a way, it doesn't really matter because you're saying if and only if. So, you know, it should be fine either way. Again, you'll usually see it written in the form if P then Q, but because they're kind of one and the same, like you can't have one without the other, they do mean the same thing written both ways, because again, both the statement and its converse are true anyway, so it's not like you'd have a false statement. Okay, so if you wrote two angles are congruent if and only if they have the same measure, you're saying the same thing. Again, if you're doing a multiple choice, it'll more than likely be written this way that I wrote it, so that's why I'm kind of following that format, but both are right. Alright, next up, again for the conditional, we're going to write the converse and a biconditional. This one I'm just going to say out, again, because we just did one just like it. So again, remember what we're doing. We got your if P then Q. That's this statement. The next statement you would need to write is if Q then P. Now this is to see who's paying attention, who actually is doing the notes here. You should write this statement out as well. Okay, so if Q then P says you're going to have an if. I'm going to have you fill it in. If Q then P says if it is Independence Day, then the date is July 4th. Again, if it is Independence Day, you're taking the conclusion, writing it first, then the date is July 4th. That would be your converse. Again, I'm still expecting that you write that. Now, the biconditional, because both of those are true, again, you could say then the date is July 4th if and only if it is Independence Day. That should be capitalized because that's a holiday. Wow, I can't write sometimes. I don't know what I'm doing. Okay, day. That's better. Okay. So again, remember you can write out the converse yourself. You can say if it is Independence Day, then the date is July 4th. And since both of those are true, we got true and true, then we can write a biconditional. Remember, the only way we can write a biconditional is if both the conditional and its converse are both true. Okay, so this is one you need to know just because of the definition. We're doing one more here, and then we'll kind of move on to something else. But this one, again, I'm going to walk through it the same way. Okay, I'm just doing a little bit less work each time. Again, at this point, I'm going to say let's write the converse out. So we got our statement, and again, this is our hypothesis. This is our P, and then we have they are collinear. That's our Q, and we're going to write if Q then P. So if, again, we said points lie on the same line. Well, what is they? They are points. So we'd start off if points lie, or if points are collinear. That's our hypothesis now, because we're flipping them. Then you can say they lie on the same line. So if points are collinear, then they lie on the same line. And think about it, if points are collinear, that's what the definition says, that they lie on the same line, so that would be true. And same thing if you said points lie on the same line, they're collinear, that's true. So then we can write a biconditional. So again, you would say in this case, points lie on the same line, if and only if they are collinear. Now you got your biconditional. Okay, so hopefully you kind of got the hang of this at this point, because it's kind of the same thing every time, right? But again, the only way we can write this is if both of those are true. And that's what a biconditional is stating, that a statement and its converse are true. So no matter which direction you're looking at it from, it's going to be a true statement all the time. So what I've been trying to get at is this statement up here, so make sure you have it if you haven't kind of figured it out already. For a biconditional statement to be true, both the conditional statement and its converse must be true. If either the conditional or the converse is false, then the biconditional statement is false. Again, you have to have both, so that's what we'll kind of test here real quick. Okay? So determine if the biconditional is true. If false, give a counterexample. So here we go. If an angle is a right angle, sorry, an angle, not if. An angle is a right angle if and only if its measure is 90 degrees. So here we're starting with the biconditional, but should it be? So we'd have to, in order to test these, what you're going to do is you're going to write out an if-then statement and test the truth value of each one. So you would start off by taking the statement, and remember this first piece, this is your hypothesis. So we got hypothesis here, and here we have its measure is 90 degrees is our conclusion. So we are going to write this statement, hypothesis, if hypothesis, then conclusion. So if an angle is a right angle, then its measure is 90 degrees. And again, if an angle is a right angle, by definition, it is 90 degrees. So this would be a true statement. Again, if that was false, I'm done. I don't need to even check anything else. But it's true, so we need to check its converse. And the converse, we take the hypothesis and conclusion and we switch places. So if an angle, don't use its, use proper English. If an angle measures 90 degrees, then it is a right angle. Again, in this case, same thing. If an angle measures 90 degrees, that does mean it's a right angle. That is actually going to be true. So this one, determine if the biconditional is true. Yes, it is. Again, the only thing that makes it true is because both the conditional and its converse are true. That's all we're looking for. Alright, next up, just to show you an example of one that maybe doesn't work. We actually had something like this in the homework before. So here's your biconditional, and what I'm going to do to test if it's true or not is I need to test the conditional statement and its converse. So here's the conditional. We're going to take the first part, your hypothesis, call this P, call that Q. I'll look at it using symbol notation now. So if y equals -5, then y squared equals 25. Now in this case, if y is -5, you squared it, that would be a true statement. I could square -5 and get 25, so that's true. We're going to look at the converse now. I'm going to flip the hypothesis and conclusion. If y squared equals 25, then y equals -5. Now this one would be false because if y equals 5, or y could equal 5 as well, so this would be your counterexample. So in this case, the biconditional, because both of these aren't true, the biconditional I didn't mean to do in all caps, I just started, so I kept going with it. Biconditional is false. Again, the reason for that is because of that truth value for the converse being false. Alright, so that's really all you need to do to test a biconditional. Just see if the statement and its converse are true or false. They have to both be true for the biconditional to work. Okay, so kind of the last little piece to go over here, we're going to talk about definitions real quick, because we're going to need to use these or we need to talk about definitions in order, or biconditional statements, I'm sorry, in order to write definitions. So again, when we start getting into our proofs, the things that we're going to need to know about are definitions, postulates, and theorems. So again, a definition is just a statement that describes a mathematical object, and it can be written as a true biconditional. Now, we actually used a couple of these, like when we were talking about the right angle being 90 degrees. That's a definition. So if it is a definition, then it is going to be a biconditional statement. Again, definitions can be written as biconditionals. So no matter which way you're looking at it, it's always going to be true. So some common types of definitions here. We have polygons. I have some more about different types of figures on the next slide, but in the glossary that we now have, a polygon is described as a closed plane figure formed by three or more line segments. Now again, it doesn't matter which way you look at it. I can write any type of conditional statement for a polygon. It's always going to be true. So again, if you look at the definition for a polygon, try to get my highlighter up here. It's a closed plane figure formed by three or more line segments. So if I wrote that out, I could say if a figure is a closed plane figure formed by three or more line segments, then it is a polygon. I could also say if a figure is a polygon, then it is a closed plane figure formed by three or more segments. Both of those statements would be true. Therefore, you could write it as a biconditional. So the biconditional would be, again, you say a figure is a polygon. If and only if it is a closed figure formed by three or more line segments. Again, this is just a helpful thing to know if you're trying to test biconditionals. Understand the definitions are biconditionals. It may not be written in that format, but it can be automatically, or it won't be a definition. Okay, some other definitions here. We got polygons, triangles are different types of polygons, be more specific. Quadrilaterals are polygons of four sides. We have a section, we'll go over that. But again, they're all definitions. These are definitions that could be helpful as we go through some sections here, but make sure you understand that definitions are going to be biconditional statements. Now that is not necessarily true if we're doing postulates, or especially theorems. So again, order does matter when we're dealing with other types of figures or other types of statements. And again, when we do proofs, the three things that we're going to need, and I'll write them out here, don't mind that. If you have proofs, you're going to need 1, definitions. Again, these are biconditionals. 2, you're going to need postulates. And 3, you're going to need previously proven theorems. And most theorems are written in a conditional statement form, like if A then B or if P then Q. So again, these two here may not be biconditionals, but that one on top, this one here, these are biconditionals. So again, that's a little helpful hint as we kind of move forward. There, okay. All right, so to kind of wrap up here, write each definition as a biconditional. So here we go. We got a quadrilateral is a four-sided polygon. So you have to write again as a biconditional. So we need to be able to figure out how we would write this as a hypothesis and a conclusion. So in this case, you can say your hypothesis would be like the figure, the quadrilateral, and then the conclusion, if you're looking at it, can be a four-sided polygon. Now again, it's not written in if-then form. You just got to find the two parts that can make the biconditional up. So what you would have to say, again, we're going to say P if and only if Q. So a quadrilateral, a figure, is a quadrilateral if and only if it is a four-sided polygon. Again, make sure when you do a biconditional it is not an if-then statement. You just write your hypothesis, you put if and only if in the middle, and you just write your conclusion. Okay, a biconditional is not an if-then statement. It is a combination of an if-then statement and its converse. All right, next one, the measure of a straight angle. So you have a straight angle, the measure of that angle is 180 degrees. Again, I'm trying to find the two pieces that make up this definition. So sorry, I'm going against my own statement. I'm trying to write the conditional statement, but we're writing the biconditional. This is a definition, so I don't need to write my conditional, my converse. We know it's a biconditional. So a straight angle, figure, oops, let me go back. I'm doing it just like I did the one above. An angle, instead of a figure, is a straight angle if and only if it measures 180 degrees. So again, typically the way I'll set these up, I'll just say a figure is, or an angle is, or whatever a shape is, and then I'll, after that, kind of mention its property. And you'll see how I highlighted the hypothesis and conclusion. I mentioned the figure as my hypothesis, the shape, and then I mentioned what properties it has as my conclusion. So that way you can hopefully get an idea of how to set up your biconditional statement. Alright, at this point we got our lesson quiz, so it's, again, real quick, just 3 questions. So make sure you pause the video, get that taken care of. That's, again, the lesson quiz for 2.4. And again, if you have Miss Moore, you have the assignment, you can kind of go over that if you need. Again, Mr. Patrick's class, I'll give you the assignment in class, so don't worry about that. The last thing we need to do to kind of wrap things up, make sure you are getting your reflections done. Some people are not doing them. Make sure you scan and get these reflections done as we go through each lesson. Alright, with that, I'll let you guys go ahead and wrap things up. Do what else you need to do.